Wow. First, let me start in German. Guten Abend, everyone. So, for the next 60 minutes, probably a bit less, we are going to talk about reversing communication protocols. But we are going to target a specific communication protocols, which is a botnet communication protocol, quite known, named Zero Access. So, who are we? First, we are French. So, sorry for the accent. And okay. Great. So, Frédéric, just here, is an IT security engineer in France. He's specialized in reverse engineering, of course. And his field of interest are the system analysis and the hardening and the trusted computing. Me, I'm a PhD student, member of the Supélec Elite School Cyber Research Team. My advisors are Guillaume Miette and Ludovic May. Hello. And I'm specialized in intrusion detection, botnet simulation, and of course, protocol learning. We are both from the French company named Amosis. It's a security company with audit and eval. Not Amosis, Amosis. Audit and evaluation. And we also do research and development. That's what we are going to talk about today. So, topics. We are going to reverse a protocol. We are going to simulate endpoints once we've reversed it. And finally, we are going to try, or we are going to map the botnet.
So, why do we do reverse engineering of protocols? First of all, protocols, you can find them everywhere. You can find them between endpoints. You can find between communication of process between processes. You can find between that when a binary talk with its libraries or with a device, for example. And you can even find protocols inside Tamagotchis, for example, if you've seen the talk of yesterday. So, why do we need to do reverse engineering? First of all, we like to do some test analysis, robustness analysis of implementation of protocols, like if you want to fuzz a control IP of a centrifuge. And if you saw some talk yesterday, they talk about fuzzing and vulnerability analysis of some implementation of protocols, like those with Tamagotchi and ES6 binaries. You may want to analyze traffic to find and to identify potential leakage of sensitive information, like if you want to be sure that your IP reputation appliance doesn't leak any sensitive, critical information. You may want to do reverse engineering when you want to compare the implementation of a protocol with its specification, like in common criteria, when you do security evaluation of products, you have to do the evaluation of specification and its implementation. And last but not least, you may want to develop an open source version, a free version of a protocol implementation when this implementation is proprietary. So you want to do reverse engineering. And if you have seen the talk of Drew Fisher last year, maybe he's here, I don't know. He talked about the reverse engineering of Kinect protocol, and it was quite interesting.
So first we are going to present the current reverse engineering approach most of you may work with. Please, can you raise your hand if you've already reversed communication protocols? Or try to, okay? Don't move. Please, did you look like this when you try to reverse a protocol? Okay. That's the common scenario when you try to reverse communication protocols nowadays. You have lots of flows, hexadecimal flow, and you stare at them for days and try to find relations, size fields, CRCs and co. That's horrible. It's complex, time-consuming. You have to be a guru of encoding to be able to do this kind of stuff, and it's mostly manual. I had it's mostly visual because you stare at bytes for days and days, and it's like this that you reverse communication protocols nowadays. So we looked at this problem and tried to think about creating a tool that would help us to reverse efficiently a communication protocol.
So this was a starting point for our research 2 years ago, and we wanted to find some way to automate the reverse engineering of protocols. So we look at some well-known protocols like TCP, and we wanted to find some characteristics that we can then automate to infer. So let's take TCP. TCP has some, you have the different types of messages like SYN, ACK, push, and so on messages. You have the notion of concept of encapsulation layers. TCP is encapsulated inside IPv4, which is encapsulated inside Ethernet. So you have layers of protocols. And inside the protocols, you have the notion of field partitionings. Messages are split in fields that have specific size, either dynamic or static. And inside those fields, you have relations. Here we have a specific relation with is the offset of the starting of the data. So it relies between two fields. And you have another kind of relation, which is inter-symbol or inter-message relation, like the sequence number and the acknowledgement number of TCP. And other kind of characteristic we can find, it's contextual values. It means values that are specific to the environment. And you have application level data or values. And last, you have some sequence of valid messages. It means the authorized list of messages you have to send to be able to talk with a real implementation. So these are some characteristics that are quite common in many protocols.
So when you want to reverse communication protocol and to help the expert when he's reversing the protocol, you need to be able to automatically find all these informations. Okay? So in order to do this, we'll find a model which will represent a protocol, and we'll create a strategy or a tool which will help us to infer or learn the model. That's good. I'm part of an academic world, and I like models, like most of the academics. And this time is not a useless model. We've taken the model from Gerard Holzman. It's a French, I think. He published a book, a very good book if you're interested in reversing communication protocols, named The Design and Validation of Computer Protocols, and he described protocols in 5 parts. You will see it's mostly academic work. A protocol is defined with a service, meaning each protocol has been created for a special purpose, okay, a special objective. This model also includes some assumptions on the environment. When you create a protocol, you create it for IP encapsulation, for example, or for wireless communications, so you have some assumption on the environment. You put in your model some messages, the vocabulary of your protocol, so the list of messages, the encoding form and the format of all these messages. You add the grammar of your protocol. The procedure rules is the academic term for sequence of valid messages. And you have a model. Okay. For us, it's way too much complicated to learn this model. We have too much data to learn, and it's quite impossible using automatic approach. So we try to reduce this model to something that we can manage. So we simplify the protocol model with 2 parts. The first is the vocabulary, the list of messages it contains, and the grammar will represent with a state machine. That's quite common. So since we've found a model to represent a protocol, we've created a tool named NetZob that we'll introduce that will help the experts to learn this model.
So NetZob is a project that we started 2 years ago. It's an open source project. It's available on internet. And it has three main goals. The first one is to be able to infer to reverse communication protocols, especially proprietary protocols. The second one is to be able to simulate and generate traffic, realistic traffic, that are understandable by real implementation. And the third goal is to be able to do smart phasing based on the knowledge of the protocol we've just learned. So three main goals. The approach we've taken inside NetZob is as either passive and active inference. By passive, I mean just observing some traces and trying to infer the message format and the grammar of the protocol. And by active, I mean talking with an oracle, a re-implementation. We use a semi-automatic approach. By that, I mean that it's not entirely automated. The expert has to do some tweak, to specify some parameters to understand and to better understand the protocol. And we don't rely on binary manipulation, either static or dynamic analysis. We only observe traces. So this is a big picture of NetZob, its architecture. It has four main components. The first one is the import component. So we have capture and importer. You can capture network flow, IPC, inter-process communication flow. You can integrate files, XML files, and you can either capture API flow. I mean API flows that are taken from the SPI project. So we handle those importer. You have the heart of NetZob, which is the protocol inference part, either vocabulary inference and grammar inference. And when you understand the protocol, you have reversed the protocol, you can either simulate and generate traffic, or you can export the protocol to a third-party product. For simulation, you can simulate a client, server, and you can do phasing. And regarding the export component, you can export to XML text format, and you can export in a few days, because it will be released in a few days, to pitch further and to Wireshark or Scapy if you want to dissect some proprietary protocols. So as I've said, it's totally open source. So it's written in Python. We have a pretty nice graphical interface. And we have also a plugin architecture, so it allows you to create some importer or exporters if you want to handle new captures, a new communication channel, or new third-party products, for example. And this project is available through many ways. This is a team that participates in NetZob. It's almost 12 people, and we have two main sponsors currently, Aimosis and the Scipelec school. With NetZob, we try to be at the state of the art in different domains, those 6 domains, and especially in reverse engineering of protocols, in grammar inference, and more for George, in the behavior analysis of botnet, command and control channel. So we try to be and to propose new way in research. So that was NetZob, the project. Now we will see how to use NetZob to reverse engineer the zero access control and command channel.
So zero access is a well-known botnet, still in activity. I think it has been discovered in something around September from the last year. And it's 2 months ago, Sophos has mapped around 1 million zombies in this botnet. And like most of the current inactivity botnets, its objective is to gain money. So it's execute click fraud and Bitcoin mining to get money. And we are interested in the two. We've looked at the 2 versions of the rootkits, the binary, and we will, for this presentation, focus the latest version of the botnet. So you have a peer-to-peer management system in this botnet. It allows to share the peer directory or to share files, and it uses UDP and TCP to connect between each zombie. Okay. Inside each binary, you have a set of hard-coded bootstrapped IPs The zombie connect to these peers, retrieves the peers directory, and can speak like any peer-to-peer protocol. So we are going to play with the peer-to-peer protocol. First, we have some requirements, of course. We need real communication traces. We contacted Kevin McNamee. He's the first who reversed the encryption protocol of the zero-access botnet. He sent us some traces, real traces. We deliberately infected one of our machines to gain more traces, okay? And we also, a few days ago, downloaded from Contagio. It's a website, a blog, where you have some samples of the any malware. And he published some pickups of zero access. So we downloaded all these three sources of traces and used them to reverse the protocol. We also used a confined environment and the binary of the malware for the grammatical part of the inference. But we won't go deeper in it because it's quite long to explain. We use, as any confined environment, firewalls and virtual machine and stuff. Please, if you do this, consider legal issues before installing before infecting your own machine with a botnet. So first, you need to extract from the traces some data flows. So this is the kind of data flows you obtain from a pickup from zero access. Okay. You split the data flow using previous knowledge of the sub-protocol use, like if it's over TCP or over UDP, over USB, you can split the data flow in messages, first message, second message. And you can also use, within NetZob, delimiter-based splitter. And you import these messages into NetZob. You can either use Wireshark and export into NetZob, or use the capture module, which sniff your Ethernet card or anything and import messages into NetZob. So once you've obtained traces and provided them to NetZob, you can start reversing the vocabulary of the protocol.
So the goal of this first step is to abstract messages. So you have raw messages, raw binary data, and this data contains some specific values that are specific to the environment, like IP, timestamp, and so on. And the goal is to decontextualize those specific values to have an abstract value of this information. And to do that, the idea is to regroup messages by similarity and to then those similar groups to find contextual variation, contextual values. In order to regroup messages by similarity, we rely in NetZob on their common partitioning. I will explain now. How do we do partitioning of messages together? We support many ways inside NetZob. The first way is quite simple. It's a simple alignment. So it's only try to separate static and dynamic variation on columns. Second way is quite simple also. You have delimiter-based alignment, so you use a delimiter and you try to split messages according to this delimiter. And the third is quite interesting, which is called sequence alignment. It tries to find the optimal alignment of two or many messages. And to do sequence alignment, we rely on an algorithm which is called Needleman and Wunsch, and which is taken from the bioinformatic domain. But what is Needleman and Wunsch? Let's see. So the idea of applying Needleman and Wunsch to do reverse engineering of protocols has been initiated by Marshall Bellow. I think it was in 2004 or 2005, something like that. The idea is when you have two messages you want to align, so that's one. You build a distant matrix, so you take the two messages and you build a row and a line. And then you initialize the matrix with some initial data, the zero. And then you have a formula to fill the matrix. The formula works as follows. You take to fill a cell, let's say this one, you have to take the highest score between the top one, the left one, or the top left one. And you, with modulo some parameters, you fill the entire matrix like this. So when the matrix is totally filled, what you do is a trace back. You start from the bottom right and go to the, try to find a path to the top left by specific values. And the idea, the goal here is to find the command pattern that corresponds to the better alignment of those messages. So here the result is simply two static bytes, the 70 and the 0, which are static, so we align them. And in the middle you have the dynamic variation, the dynamic part, which will then correspond to a unique field. So here you have three fields, the 70, the dynamic part, and the 0, which is another field. Based on this information, based on this command pattern, in order to manipulate that inside a NetZub, we rely on regular expression. So we just compute a basic regular expressions that corresponds to this alignment. So this is the regular expression of this alignment. Here, with regular expressions, it helps inside NetZub to do field partitioning, to split messages between fields. So with this information, we can easily split messages with the inside NetZub with the 70 and the 0. In the middle, you have the dynamic part. So you have the static fields and the dynamic fields. Okay, so now you are able to do partitionment of fields with many messages. So let's see how to do similarity with them.
We need to, since it's an automatic approach, this part of the algorithm, we need to automatically find if the alignment is efficient or not. Okay, so we qualify the alignment with a score. We name it the similarity score or measure. And we compute it for each pairs of messages and try to find the best alignment using this score. So we define a similarity score. If two messages has a 0 for similarity score, it means they have nothing in common. Whereas if it's 100% similar, it means messages are almost identical. So we define few scores or ratios we use to define if the alignment is efficient or not. We won't go too much deeper in these scores, but we allow it to create and add any additional factors we could that you would be interested in. So the first factor or score is the ratio of dynamic fields over the total amount of bytes, whereas the second similarity measure, I would say, is the ratio of common dynamic bytes over the two messages. You take these two factors, you normalize, compute the similarity score here, and you can have, with this solution, a number between 0 and 100 that you can use to compare between other pairs of messages. This will bring us to the clustering process of the alignment. So we use a UPGMA clustering algorithm, famous. It's a hierarchical clustering. We put all the messages in a matrix, okay? We put the similarity score. So here, this message is 50% similar with this message. And we find the highest score and reduce by matching the messages the more common and reduce the matrix. Okay, it's an iterative process and it allows to find similar messages which have similar alignments. Okay. It creates similarity tree. It has a very difficult name in bioinformatics. I don't remember it. Phylogenetic tree, yeah. And using this tree, we can find clusters and find equivalent messages automatically. Here we have 1, 2, 3, and 4 clusters of messages. This means that all the blue messages are identical, for example, and the pink messages are mostly identical. That was the theory aspect of the clustering. When we implemented these into NetHub, we used this kind of graphical representation. You have all the messages here, and on the left part, the clustering, so the groups of messages you are looking at. So once you've obtained clusters of similar messages, and once you've find fields into these messages, you need to understand what do they contain, what's the meaning of each byte into the messages.
So before going further in inferring the characteristics of the field, let's see what is the model we use inside NetHub. The top part of the model is quite simple. You have raw messages. These raw messages can be split in layers, in protocol layers. Like, for example, you can have Ethernet and here IPv4. And each layers can be split in fields. It's quite simple. This partitioning, this strategy of multiple partitioning allows for multiple partitionment elements, for example. And this is a complete part of the model. So for each field, you have some specific attributes. You have the attributes that are specific to this side, which can be either fixed or variable. You have some interpretation attributes, how to interpret raw bytes either as integer, string, ASCII, and so on. The indianness is a sign, for example. You have some transformation attribute. We will talk about that just after. And you have the definition domain of the field, how it varies, what is authorized values for this field. This field can be static, random, and can have some dependencies on other fields or on other messages. And you have an optional characteristic, which is a field, which is a semantic, sorry. And the semantic is optional because you don't always need to understand what is the meaning of a field to generate traffic. You can just replay traffic and it will be okay for real implementation. So this was quite a tough explanation. So we wanted to, because we have 60 slides left, we wanted to make a small pause, a small interlude. So we'll do during 5 minutes some knitting. I'm kidding. So, how does the transformation work? And why do we need transformation? Because you have some raw binary data that are, we don't know what is it. And in fact, in reality, the meaning of those bytes is interesting when you have the clear text. So you can have encoded data like ZOR or the grammar SN1 encoded data. And you can have encrypted values, like if you have XOR-based encryption, like we will see just after. So we have some transformation to handle to obtain the clear text of the data we want to analyze. To do that, we have and we support transformation functions. I mean some functions you can implement inside NetHub to transform data to application level bytes. So you can either apply those transformation functions on messages, layers, and fields, and you can, with NetHub, use provided functions. We support some base 64 conversion and some zip compression function. And what is interesting here is that you can add your own custom transformation function. This is what we did for the zero-access botnet communication channel, because it uses XOR-based, a really simple XOR-based obfuscation function. So inside NetHub, you can add your own code in Python, in the graphical interface, to transform some raw messages inside clear text messages. And then you can work on it to understand the meaning of the field. So let's see now how to handle relations.
Okay. So before relations, the expert has quite a good view on the vocabulary of the protocol. He's reversing. He has the messages clustered in similar groups. Okay, each message has been split in fields, and he has a bit of a knowledge of the evolution and the variations of each field. If it's a static or if it's a dynamic field, if it's smallly variated or not. But there is something every reverser is looking after, is to find automatically relations. That's the kind of problem when you have a value that depends of something else, like when you have a field which contains the binary ID of the botnet, it contains the file name, the affiliate ID, or when the field contains the value of the size of another field, or if it contains a CSC of another field. That's the kind of relations you have always in protocols, and that you want to find and to reverse when you are looking after an unknown protocol. So how can we reverse automatically, or how can we help the experts to find these relations? We use the maximal, I'm sorry, it's maths, maximal information coefficient correlation system provided by the MIT. It's very efficient. It allows to correlate the value of multiple fields and to find fields which are highly correlated. Okay. Once you have these pairs, you can qualify the kind of correlation and compute if it's a size field or if it's a CRC or something else. It's quite simple. For each field, you generate a set of data. Like you take the value of the field, you take the size of dynamic fields. You have more data, like you concat fields one with the other and compute their value, their size. You create n-grams. It's when you split data in short segments of 4 or 8 bits. Or we also consider the CRC value of a field or the MD5 value of a field, and therefore. When we have computed all this value, we find for relations between these values using the mine algorithm. So we measure the dependencies between each pair and we rank pairs by the score. Two simple examples. We compute the mine of the value of the first field with the size of the second field. The score is 1, the maximum. It means it's a size field. Okay? It's quite simple. Another typical relation is the CRC relation. We compute the correlation factor between the value of the field and the CRC32 of a set of fields. If it's a high score, it means it's the CRC relation. So that was for the normal relations in protocols. We have another set of relations which are the environment dependencies. It's when the value of a field depends of the context, like the hour, what time is it, if the protocol sends the timestamp or if it sends the IP address. That's the kind of environmental relations you have in common protocols. So in order to automatically find these relations, or to help the experts find them, when you import data into NetZob, we store lots of metadata, like the current dates, the current protocol, sub-layer protocol, the IP address if it's a network protocol, the name of your Windows session, for example, this kind of metadata, and we search them into your vocabulary. Okay, that was the vocabulary inference. There are more features. We won't have time to go deeper in them. We'll show you a short demo at the end. I'll speak about grammar inference now. The grammar of a protocol is the sequence of messages which are exchanged, like the three-way handshake in TCP, okay? So how can we automatically infer the grammar of a protocol? We use an automata. That's quite simple. You have two states, for example. when you send attack, you expect to receive success. And that's the common definition for I/O automata, input-output automata. We change it to a different model. We name it SNNDT. I won't tell what it means. It only includes a probability. Okay, so when you send attack, you have 80% chance to receive fail or to receive with 20% the success. We also included the reaction time into the grammar. So when you succeed, it's often more fast, for example. And when you fail, it can be a 2-second operation. So that was the model of the grammar. This schema now is how we can infer automatically the grammar of a protocol. We use the Ungreen L-star algorithm, famous. We have a learner, your computer as a reverser. It sends queries to a confined zombie. So you put your malware into a virtual box, you send data to the malware, and you, using probe, external probe, you compute if it's valid or not, if it answers or not. Given all the information you retrieve, you create an hypothesis model. And when this model is big enough, you can compare it to the real one. I won't go more in it. We have implemented this algorithm and some little tricks in it into NetZob. If you want to test it, you can don't hesitate. That's the kind of results you obtain. It's a very simple grammar of the zero access protocol. It opens a communication channel. It sends and receives something with, it's small, with different probabilities, and it closes the channel and turns like this. Very simple. So now that we've inferred the vocabulary and the grammar part of a protocol, we'll show how we can generate traffic.
So the simulation part of NetZob is interesting because you know the protocol, you infer the protocol, so now you can generate traffic. So you can simulate either a client or server, or both client and server inside NetZob, and you can talk to a real implementation if you want. You have to understand the distinction between a client and server and the initiator and responder of the communication channel. For example, you can have a TLS session, that is that the TCP session is opened by the server. So we handle such characteristic. We also handle the abstraction from the communication channel. For example, if you want to send TCP messages over a USB channel, or if you want to send IPC traffic over a file, let's say. We use a memory mechanism. We use it to memorize previously seen fields, for example, like IP, that we want to re-inject in future messages. This is quite interesting, and I will show you an example here. So this is a simple generation of traffic of the zero access communication command and control channel. At the input, we have raw binary data that is taken by the communication channel of NetZob, and then by the abstraction layer, we are able to understand what is the message we've just received. We have a getL symbol, which means it's a peer request. The peer request for other peers. It's a peer request. And we send this information inside the grammar model, the state automaton. And this grammar model tells us that if we receive the getL symbol, we have to send the retel symbol. So thanks to the model. And then we can we can send the retel symbol, but first we have to contextualize it. So we send the retel symbol inside the abstraction layer, and then we send the retel symbol inside the abstraction layers, and inside the abstraction layers we use the memory that tells us that we have seen some previous IP, and we use them to build the message, the packet. And then we send them inside the output device. Okay, so this was the simulation part of NetZob, and now we'll show you some demo.
We didn't want to do it live, to do live demo, so we captured our screen during the demos before the current talk, and we'll show you the video. The first video is halfway, 2 times faster than the reality, only for timing problems, and the second video is a normal time. So here it's the NetZob application. We create a project. Sorry. Okay. We select pickups to import in it. Okay. So we selected a pickup. We decided to only consider the UDP sub protocols, and we select messages we want to reverse. Okay, so we select every messages and import them into NetZob. Okay, so that's the normal view for reversing a protocol. You have all the messages in a hexadecimal flow, and you will try to find all the stuff we've presented just before. So the first things every reverser do is to decrypt the protocol. So here we select the Kevin decryption routine and insert it into NetZob and apply it. So here we have the encrypted imported data, and here is the decrypted data. Okay, so we can close the encrypted and work on the decrypted. Here it's the byte distribution view. We have here the first byte of every messages. Here is the last byte of every messages, and their values are here. So this graph is very efficient. It tells us that here we have something highly compressed or highly entropic, or which value varies quite well. And here we have something we might be interested in looking at, because there is a pattern in the field value, and we will try to understand why this protocol looks like this. So we execute the clustering and sequence alignment algorithm. It's not so, doesn't take too long. And we obtain 2 clusters. The first one here only contains 1 message, and the second one here contains 26 different messages. This means that these messages is very different than the others. So we'll consider the 26 other messages. Okay. And as we can see, the messages has been split in fields, dynamic and static fields, and we'll now try to understand what does these fields mean. We can change the visualization format of the fields, like here in string. We can find that it's a retel message. It's when you finish to reverse the protocol, you name this message retel. So you renamed it retel. This one was the getel message. So we can come back to the byte distribution view and show that we've found a lot of fields in the specific part we were looking at. And now we'll execute the environmental dependencies research. This means that we're going to search for lots of different data into these messages, like the timestamps, the layer 3 destination address, or other stuff. And it tells us something like 83 occurrences found. We search for them. Okay. Here in green, it tells us that it's the hexadecimal value of the IP address we've captured. So we can say that this field, it's an IP field. We can change the visualization format. And we have here all the IP of the protocol. We can apply this to all the fields. And it's the peer exchange for these messages. Okay, that was a simple view of the reversing the zero access vocabulary protocol. And now we will show you how we can use this to Thank you. We'll show you how we can use this to simulate fake zombie in order to map the botnet. Sorry. So this video was taken a few hours ago in the conference. Sorry for the traffic. So we created a very simple grammar. It opens a communication channel, send messages, and close the communication channel, and reopen it and open and send messages. So we are going to retrieve all the peers of the botnet just like this by sending getel messages, parsing the responses, so the retel messages, identifying in it all the IP address we received, and use them to reconnect to this IP. Okay, so that's the initial state of the grammar. We will start by the S0. It's the number of attempts and the time before opening the communication channel. That's the transition which allows to send a message and to expect something in response. And that's the close channel transition. Very simple. So based on this grammar, we will create a simulator, botnet actor. We give its name. We say it's an initiator, meaning it's our actor which will start the communication. Okay, it's us who will send the first message. We say it's an UDP client, and we say here the first that's a real botnet IP. So we'll first start by this IP and retrieve its peers and try to map the botnet based on this American IP, I think. Okay? Just before I show you that there is nothing Wireshark. And we send getel, and we start to receive retel, and we do this very fast. And we can see that we send UDP packets and receive UDP packets from the botnet. This means that we efficiently reverse the protocol because we are able to generate valid and realistic traffic. That's the getel message we sent, and that's the response. Okay, and we just extracted all the IP from this communication, so it was a 2 minutes mapping attempt. And we created a small script in Python to display the results over Google Earth, just for fun. Sorry, this was over a Windows computer because Google Earth wasn't working on a computer, so it's a different video. So we open the generated file. It takes a few minutes. Okay. So it's a 2 minutes mapping of the botnet, and we have all the red points, which are the actors of the zombie. Most of them are in US or in Europe. Here it's the US botnets. Here we didn't hide the IP address. I don't know if it will cause us a problem, but. And that's the Europe We will just have a look at the Hamburg city just to see if someone in Hamburg has been infected by the botnet. And yes, this IP has been infected. Okay.
Okay, some few words about the future of NetZub. We saw the inference part, the simulator part, and now we want to focus on fuzzing proprietary protocols especially. So we want to insert the fuzzing characteristic inside NetZub, and this will allow to fuzz undocumented and proprietary protocols. We also want to support more communication channels. So if you want, especially and thanks to our plugin architecture, we can easily integrate a USB IOCTL capturer, for example. We also want to support more export plugin to third-party products, and we are at many days to release some plugins for Wireshark, Scapy, and Pitch Fuzzer. So for Wireshark and Scapy, this will allow to dissect, to analyze proprietary protocols or undocumented protocols inside well-known and established tools. And for Pitch, this will allow to fuzz proprietary protocols with well-known and established tools. Okay, this is future NetZub, and if you want to contribute to write your own capturer or exporter, we'll be glad to help you. So, some few words about the conclusion and some insights. Protocol reverse engineering is quite active at the academic level, but very few active at the hacker level, because we only reverse manually or visually. And as our knowledge, we are not aware of other tools that provide vocabulary inference and grammar inference. So I think it's quite interesting to fill the gap between academic and hackers domain. We are also open to all kinds of contribution, especially if you have feedbacks. If you want to try NetZub, we encourage you to try it and to give us some feedbacks. If you find some bugs, because there are some bugs, you can provide some bug fix, and especially feature proposal. If you have some ideas, some stuff we didn't implement it, so it will be interesting to hear from you. And we also support some translation, so we support French and English. And if you want to write your own language translator, it's okay. So if you have any questions, we'll be glad to help you.
Thanks, George and Frederic. So now we're opening to questions, and you're finding the microphones. You know the drill. All right, let's start over here.
Hi, thanks for this tool. I think you just got this download spike, but okay. I was wondering about the external dependencies. So for example, lots of protocols are timed, so dependent on the external clocks, for example. How well does your tool handle that? So the communication needs to be slotted, time slotted, for example.
Okay. Time-based protocol are quite difficult, of course. It's why we edited the IO automata grammar state machine, and we added the reaction time coefficient into the transition between states. This means that if a message is valid only after a break of 10 seconds, we can create this kind of transition and support this kind of protocols.
Have you tried it on some time protocol?
Yep. Any more questions?
Hi, first, it's an impressive work and thanks. The second is that the protocol you showed us is essentially a binary protocol. What about text-based protocols?
Yep. We think that binary protocols are more difficult to understand. So here we showed quite interesting protocol because it's well used in malware activities, but we can easily work on the text-based protocol, especially with the sequence element, because binary protocols it's better to use a simple element or a delimiter-based element. But for text-based protocol like HTTP, FTP, ERC, it's really easy to use sequence element. So you have a really good understanding of the fields partitioning, and then it's quite easy to understand the meaning of the fields.
Thanks.
And we have a question from the internets. We have 2 questions. Let's do one at a time.
3. Okay, the first one was, what does the ZOP part of NetZOP really mean?
They can be really creative.
It means officially network modelization by reverse engineering. You need to find letters and you combine them and it creates network.
All right, based on the quality of that question, let's go back to the room.
Really great tool. It feels it fills a space that hasn't been yet filled by tools. So it's really useful. You meant it as a general tool, right? For not only for the specific protocol of the botnet, but for general users. Right? So, are you planning to implement protocol decryption? It also wasn't really clear from the presentation, from the video, how you decrypted the protocol using this tool. I have, of course, Skype in mind, which has heavy encryption before even you can start looking at fields.
Okay. It's not magic. We cannot reverse the decryption routine of the protocol. So in this example, in zero access, someone gave us the XOR-based obfuscation algorithm, and we inserted into a transformation function, and we apply it to the communication protocol. So we don't decrypt automatically the messages, but we'll help you to try different kind of encryption, and we'll help you to try to apply in different orders. So you can change everything, the endianness, the byte order and everything, and you can apply different kind of algorithm. But we won't be able to find automatically the private key of the Skype or something like this.
So there is some kind of interface to do that, to enter the algorithm yourself.
Yeah, there is in the slide. There is we shown how we created the transformation function, and this was the decryption the place where you can put your Python code to decrypt a field, a layer, or all your messages.
And I'd also like to add a note that I think this tool is quite universal. You can actually, it looks to me, you can actually use it for mapping wire protocols. For example, JTAG, some custom protocols and stuff like that. Yes. Thanks.
Yeah, we really would like to apply this tool to any kind of protocol, not for language protocols, but for informatic protocols. I think it can apply to files, to configuration files, for example. It can apply to IPC exchange. It can apply to network messages, of course. But for any kind of communication protocols, you can use it to be more efficient into your work.
All right, let's take another question from the internets.
Second one is NetZOP usable as a Python library, API, or just through the GTK UI?
It's not yet implemented, but we really would like to create an API and to be able to use only your Python console and to reverse your protocol without the graphical interface. but it has not been yet created.
So the internets have redeemed themselves. Oh wait, I think you're here first.
Okay. Great work. Can't wait to try it. Did you say there was support for reversing binary file formats as well, or?
Yes.
Yeah.
Yes.
Great. Thanks.
Welcome.
And that's how we like the questions here, short and sweet.
Okay, thanks. Really great work from my perspective. The thing is, you started to invent this method to reversing a binary protocol. So the thing is, you can only start with a method if you have some binary stuff on the one side and one clear text stuff on the other side. What do you do to prove that it works? You use TCP itself, or what was it?
You mean if you really reverse the protocol, if you understood the protocol?
How do you prove the correctness that your method is working?
A way to be sure that you really understood the protocol is to use a simulator engine and to talk to a real implementation. And if you can talk to a real implementation, and if it answers you, and you can guide it to a specific state in the state machine, I think it's a good proof that it works.
I know completely that it works, but you have a start point from something binary, and then you have something, I think on the other side, more or less a clear text like TCP, or everybody knows how TCP works. So what you used to start this, only the proof that the point on the other side is reacting to you, or I want to see, in the end, I want to see how powerful this tool is.
To answer the first one, we would like to create an exporter for Wireshark, because it would allow us to compare previously created dissector for Wireshark, the official one, with the automatically inferred and created one. So if we can compare the Wireshark dissectors of the protocol, and if the two matches, it means the reverse went well.
Yeah.
And for your question, I think you're talking about the grammatical inference part.
Yeah.
We are never sure that the message we sent generated an answer or not. We have some time measures, and if we did not receive something between the first or the second seconds, we consider that the message was wrong.
Okay. Okay, thanks.
And we have one more question from the internets.
Yeah. Are there any plans to support passive grammar inference in NetsOp from network traces without any active stimulation?
Yes. That's funny, because that's exactly what I'm doing now. Because the active aspect of the grammatical inference is quite heavy. You need a confined environment, you need to put your binary in it, and you need to send experiments and go. This is very efficient, but time consuming, and you often do this in the end part of your reverse engineering. But the passive inference of the grammar would be very fast, very, very fast, and it will be completely automatical. So when you start NetSub, you will have all the messages listed, and we could apply the passive algorithm to show what we obtain, the maximal grammar, a simple grammar that would explain what you've imported. So yes, we are planning to add passive grammatical inference in NetSub.
That was an excellent question from the internets. I'm impressed. All right, we're a little bit over time, but there's nothing else in this room, so if anyone has to leave, please leave quietly. Otherwise, Another question.
Hi, how can I protect my botnet from being detected by your system?
Use better encryption.
I would say you have to try. You have to try the tool, and it will help you to perhaps do these kind of things.
More public key.
Yes.
Is there a mechanism to feed this into intrusion detection systems and so on?
This is also our plan to work on generation of IDS rules based on the reverse engineering of protocols. So we will try to work on this in the next year, but it's too early for now to say more thing about it. Yeah, but it's very interesting, and we really want to do that. Yeah.
The Bro IDS. Sorry. The Bro IDS has a perfect API which will allow to insert our protocol in it. So we are looking at it.
Any more questions?
Anyone here? Okay. One person will ask two questions. First, how does NetSub handle IP fragmentation and TCP fragmentation? And the other one was, can you import XML files, not only PCAP?
Okay. For the first question, it's very simple. We use the libNIDS, the library, to reconstruct the fragmentations, but we are not very interested in dealing this for the moment, but we plan to work on it to be more efficient. And for the second question, of course, you can import binary files, PCAP files, but also any string files, like ASCII files, like an XML or anything.
Any more questions?
Yeah, if nobody bothers. The internet would like to congratulate you for making your work open source. And I should ask you if you are aware of Canapé, because IRC is questioning itself whether both the two tools are getting or aiming at the same goal in a way.
I think Canapé is quite complementary to NetSub. It's a very two different approaches. Here we try to provide algorithm to help in the inference of protocol, in semi-inference of protocol, in semi-automated inference of protocols. In Canapé, if I understood correctly, they try to provide a debugger where you can put your own breakpoint, where you can you can modify traffic or generate a specific state machine. I think it's quite, there is no the inference part, the inference of the protocol part. I think this is the difference.
All right. Thanks for all the great questions, and thanks to Frederic and George.